Alright, so now we've been talking about Laplace, 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 and then we even looked at one somewhere, and then we used it to describe why the Laplace transform is useful in some cases where we want to see what's happening in the system, right? So here we said we have the differential equation. This is basically a third order system, right? With this differential equation, we transform it, we get something like this, and then if we put a particular time t inside, right, we get to know what's actually happened to that quantity at that particular time when t, or when the time is 2 units or whatever, millisecond or whatever it may be, right? So now we are going to do an actual example, right? And here's the case where we have the, what do you call it, we have the system already modeled, right? Meaning that we have it represented by what? A mathematical equation, which is the differential equation, right? So here we have, let's see, who's going to solve this? So what the Laplace transform does, we know what it does, right? But here we are going to go through the actual process of doing it when we have the differential equations. And then we are seeing when we are doing the Laplace transform, we need something we call initial conditions, right? When you look at the order of the differential equation, it can tell you the number of initial conditions you need to solve it, right? So here we have the order is 3. That means that we need 3 initial conditions to solve this, and we are seeing all these initial conditions in this case are 0, right? So now let's solve it. Fine. So what the Laplace transform is saying is that for whatever the function that you have, you can transform it into Laplace domain, because here we have t, right? And then this t represent time domain, right? This t time domain, right? And so we can transform the whole function, yeah, the whole equation to Laplace transform. And we are seeing that basically there's a table that describes all this, right? There's a table that describes all this. So let's see how the table looks like, right? Basically there are rules like how we do differentiation and integration. There are also rules for Laplace transform as well, right? Fine. But then before that, let's identify how the terms are. So this first term in the equation here is a derivative. This is a derivative. This is a derivative, right? This is just algebra, and this is a constant, right? And then the Laplace transform says that for any function or for any term of this form, there's a way of transforming it. So we know these three are derivatives, right? So to have its own way, there's just a constant attached to a variable, right? And to have its own way of transforming, there's a constant as well, and to have its own way of transforming. So this coefficient attached to a variable, right? Fine. So now which one should we look at first? Let's look at the ones for constant, right? So this is the table. It may look huge, it may look scary, but if you know what you are doing, you'll be able to do that. But let's look at what's happening. In the table, this side is what we call the function, right? And this side is the Laplace transform. So as you can see here, let's zoom in. So as we can see on this side, it is clear that this is in time domain because of this t, right? Fine. And then what we have here is in Laplace domain has s, the same thing here, time, Laplace, right? So now we are starting with a constant first. We're saying that if you are trying to transform a constant, which appears to be something like this, right? So we know, as we here, this is just a, where we are saying that it's in time domain, time is greater than or equal to 0, right? When you do the Laplace transform, you get something of this sort. Right, so the constant, you put s at the bottom. So that's fixed for that particular one. Should we write it? Okay. So now we know when it's a constant, we know how to transform it in the Laplace domain to the Laplace domain, right? So we know that this is the constant. So let's put dashes to make our work easier. Fine. So time domain at the top, and then we have Laplace domain at the bottom, right? Is this not working? Uh-huh. So we've seen how the constant is transformed, right? Look at this table. There's a constant. When you Laplace transform, it is a on s, right? So clearly this becomes what? The constant, which is 2, becomes 2 on s, right? And then we have our equal to here. Fine. Now let's go to this one, right? 2x. When you go to the table, where do you see a constant in it? And here, let's pay attention to this. The We know that the x is the variable, right? Or yeah, the quantity that will be changing with time, but t is the time, right? So let's see. So what this says is that, how do you think you'll be able to find that one? What's your say on this? All right. So basically, you clearly see that this one is just uh the one that will be we are doing the transform is the x, right? So basically that would mean that we have a function to be in this form f of x, but on the table the function is f of t, so you have to take note of that. You know, it's not because the t appears here and then this one, this is just time, right? So you must take note of that, else it might look a bit some way, but we have to understand what's happening, right? Fine. So it's saying that when we have something of that form, when we transform it, right, you just transform the x and then you attach the constant to it, right? So basically there's a constant with a coefficient attached, a coefficient of 2, and then there's a constant x, right? There's a constant x. So let's see. So for that one, let's see if we can find it. Is it? Yeah, there's it. So a is a constant and is attached to a t. Let's zoom in, right? So a is a constant, which is the 2 that we are seeing, and then the t is the variable, which is the t, right? So when you are transforming that one, it appears of this form, right? So clearly the table can help, but when you do it, you get to a point where you know what you're doing, right? So we have 2, and then so we have 2 here, and then we have one what, s squared. This is s. We did know the Laplace domain, right? And now we move on to the derivative. For when we are doing the Laplace transform derivative, the general form is this, right? So let's look at this side. Our focus now is on this, right? And though we see the, if you understand this one, you won't have to like memorize any of these ones, right? Whatever the order, you still be able to do it, right? Whether fourth or fifth. Fine. So it's saying that when you're trying to do the Laplace transform, it depends on the order of the system or the order of the derivative, right? So here, let's take some notes of some things. So you see that if nth order, right? Now let's even use this one as an example, the second order derivative as an example. So this here, right? And then let's take note of some things to make it easier for us to understand, right? Fine. So what's happening here is that if you look at this carefully, you see that the order of this is 2. Oh, the order of this is 2, right? And you clearly see that aside this, let's now pay attention to the s, right? You see that the highest power of the s that happens is 2. That's one thing you must take note of, right? Fine. And then if you take this one out, you mean that, as we said, you need the order of the function will tell you the number of initial conditions that you need. So you see initial condition 1, initial condition 1, right? Initial condition 2. And then we are going to do examples of these to actually see what's happening. So clearly if the order is 2 and the s highest power is 2, but then another thing happens to the s. Let's see. You clearly see that the power of the s reduces until it gets to 0, right? So here s is 2, here s is 1, and here s is what, 0. In now to power 0 is 1, right? So that's why this one is taken care of. It doesn't show here. So that's one thing you see about the s, right? And when it comes to the function itself, right, we clearly, so if you figure out the s, you will know what you must add. And then here the first one is just plus, the next minus minus, fine. And then we talk about the s, and for the function the first one is f of s. The following ones are just what do you call it, the initial conditions, right? The initial conditions. So we solve examples. We'll solve this particular one to know how we go about it, right? So now let's take this one, which is the third order derivative, right? So we are going to apply the rule to see how we go about that one. Fine. So for this one, for instance, what it says is that if you are trying to transform this, which is represented this way, Laplace transform, right? This is what we have. We talked about the s, right? This is the Laplace domain. So it will have the same power as this here, which is 3, right? So first of all, we have s cubed, and that will mean I will have a minus here, right? Let's just put it here. We know all the rest subtracts, right? Let's put it here. The next s will be s2, right? Let's bring it down so we can follow what we are doing. Okay, trying to make it in such a way that be able to recall and use what we are doing, right? Okay, and then here we have s1, and then here we have s0. Right. You don't have to do this all the time, but we're just building on what we discussed so you can understand what's happening, right? Then this will happen to the x, and the first one now be attached to the, what do you call it, the s cube will be this f of s, right? And then we said the order determines the number of what do you call it, initial conditions you need. Fine. And then there's what, order 3, right? So we'll need what, 3 initial conditions, and the first one starts with this, and here we have what, x. So let's use x, right? Let's use x so we follow what we are doing. Whenever you do the transform, so let's talk about this. Here the variable is x, right? Just a minute. The variable is x, and usually what happens to Laplace transform is that when you have x, let's something like, let's see x, and do the Laplace transform, the letter becomes sort of capital, right? And it has this x inside attached to it, but this one is x of t, right? When you look at the table, you see a similar thing. So here we have f of t, the f changed to capital. Let's zoom in. Here we have f of t. These basics are important because going on, you'll be seeing them a lot, and when you understand that, you'll be able to move around any problem easily. Small f changed to f of capital F, and then the t changed to s, right? So this is what we are talking about. Fine. Yeah. So now we are on this one, right? And then when we do the Laplace transform of that, here we get, so let's see. We've already done for the powers of the s, right? So here we will have x, let's make it capital, right? And then here we have x, and we need 3 initial conditions, right? So to start with the one that has no derivative, so that will be just x of 0, right? And here we have x first derivative 0, and then here this minus, and then we will have x second derivative of 0, and then we've been given these initial conditions already. Where are they? Oh, they were here. Yeah, these are the initial conditions. This, it is not always 0, but you just have to use what's given. Right, so this is, yeah, this is what we are using. Right, so these ones are the initial condition, not the Laplace transform, so they are not capital X, right? So they have this form, just small, right? Yeah, let's write it small as well, right? So this is how it is going to be, right? And then we already know that these initial conditions, all of them are 0, but it's not always 0. Let's take note of that. So it will mean that all where they appear in this equation will be 0. So we end up with, let's see, so this tends to 0, this tends to 0, this tends to 0. So that will mean that the Laplace transform of this whole thing, this whole derivative, will end up being s cubed, right? And then we have x of s. That is what we have, right? And then we are going to do the same thing for the second derivative, right? So we have 4. So let's see. So here we have 4. So we are done with this. Oh, yeah. So here we have 4, the x squared, this squared x, then you have the t squared, right? So this is how we go about it. So here what happens is that basically if you are transforming, doing the Laplace transform of this, the 4 is just a coefficient, so the 4 is attached, and then you do the Laplace transform on the inside and you expand as you want, right? So we know, so now that we know how this whole thing is going to go, if you try it for the third order derivative, you should be able to do this one. So we know here will be s squared, right? And then we will have x of s. For the sake of understanding, should we make it cap? Let's make it x, right? Fine. So we've done this, and then uh, we need two initial conditions. So first minus, and then we need s, and then we need what, x of 0, right? And minus s to power 0, which is 1, it goes out. So if you want to make your work easier, just write everything and then do the simplification later, right? So this is 2, this is do this power 2 here, power 1 here, power 0 here, right? Because now you're starting the whole process, you should be able to write this to make your work easier, right? So x of 0, and then we have here, we have what, x second derivative 0, right? When we expand this, we clearly know that this is 0, this is 0, right? Because of this derivative, initial conditions, right? So we end up with what? We have this being equal to 4, right? x squared, and then we have what, x capital of s, right? Fine. And then that will mean that the next one will be way more easier, right? The first order derivative, there we have 5, right? And then we have the x, and then we have the t. So clearly here we know that if we are doing a Laplace transform, we need only one initial condition, right? Fine. So doing this, that will mean that here we have 5 attached. Let's write it one by one. This one, let's just write it for it. So that will mean we have 5 in the bracket. Here we have s, right? And then we have what, x of s, right? And we only need one initial condition, right? So this is to the power 0, and this is what, x of what, 0, right? And we know that this tends to be 0, right? So this goes out, and then we end up getting it to be 5s. Let's write this 5 4. So 5s, and we have x of s, right? So this is what we have. So putting all this together, we end up getting this. So basically, we've done the Laplace transform of the initial function differential equation that we had, right? So now that we've done the Laplace transform, basically we are done with the Laplace transform. So now we are going to do it so that we get it what we call the inverse transform, right? So clearly when we did that example earlier, we said that we did the Laplace transform so that we don't want to do the whole lot of integrations, right? We do Laplace transform, and then we do the inverse Laplace transform, right? So we can get in terms of t again. So when we have a particular t, let's say t is equal to 2, we can find what it is, right? Yeah. And before we do that, let's see. That will mean that we have to make what, x of x. We have to make x of this x the subject, right? So basically we are not done with the Laplace transform. We've done the transform, but we have to make x of x the subject, right? So let's see. So on the left hand side, let's see. So we have x of x, and here we have what, s cubed plus, we skip this were pluses. Yeah, there were pluses. Yeah, there were pluses. Yeah, pluses. Yeah, pluses. Fine. Right, and then we'll have 4s squared plus 5s, and this is a plus, and then we have one here is not part, it doesn't have x of x, and then we have plus 2 on s squared being equal to 2. Right, 2, when we do the Laplace, it should be 2 on s. Yes, 2 on s. So this is 2 on s, right? Fine. So now that we have this, our aim is to make that one the subject, right? A minute, when it comes to this, that x is not, there's a problem with this. See, what we were doing a Laplace transform, we said that this t here is basically the time, right? Where is it? Yeah, when we go here, we said that it is similar to this one. Where is it? Yeah, similar to this one. Yeah, we said it is similar to this, right? But there's a slight difference, right? That's why it's very important that you pay attention to the format, right? So when you look at this one very well, you see that this x here, the function is as a result of time. So this is time, right? So you see time here, this is time. And what we are having is what? It's in the format of ex, where the x is not time, but actually a variable. So the transform is not of this form. So what we are looking for doesn't appear here. But when you have it of this form, right? This is a constant, this is a variable, not time. So the transform is of this way. We have it to be 2, and then we multiply it by x of x. So basically you're just having x and you transform it, it becomes capital X of x. That's what it means. Alright, so the transform is of this form. Not what we wrote earlier. That's why even if you are using the table, you must pay attention to all these, right? So we have 2 and you have x of s, right? So that would mean I will still have 2 on the inside. If we do the factorization again, yeah, so we have 2 on the inside, and here always like this. Fine. So x of x, and then we say, what do we do here? So if we have it this form, let's say L, and then and let's say the something, the t. This is what we call the Laplace transform. So this is how we represent it. But then if we have something like this is just L. But if you have something like, let's say L and C exponent minus 1, it's what we call the Laplace inverse. And you perform it on the Laplace transform to get the origin, to get it in time domain, right? So this is the Laplace transform symbol, and there's the Laplace inverse symbol. Fine.